And then we talked about a lot of algorithms for working with graphical models. So the first sort of algorithms would be things like representing, figuring out properties of the distribution that you represent. So things like what variables are independent of what other variables, or what variables are conditionally independent of what other variables. So these are things like d-separation. And then the other thing that we looked at in graphical models is algorithms for doing inference, meaning answering questions about what is the conditional distribution of some variables given some other variables. And the basic algorithm for that was variable elimination. And variable elimination, you can think of it as basically just a way to organize a bunch of applications of Bayes' rule, or you can think of it as a way to organize a large set of summations, right? So in order to figure out the conditional distribution of these 5 variables given these 5 other variables, you've got to marginalize out the other 90 out of 100 variables. And that marginalization is a bunch of sums. And so what we want to do is to be able to do all of those sums without ever working with the full joint distribution. So like I said, variable elimination is the basic algorithm for that. We talked about as well the belief propagation algorithm, which you can think of as being built on top of variable elimination. And we talked about the idea of a message. A message is one of the, well, let's see, there's 2 ways to think about a message. A message is one of the tables. Mechanistically, it's one of the tables that we compute during variable elimination or belief propagation. Intuitively, what a message is some information about the joint distribution of a subset of the random variables. So during belief propagation or variable elimination, we work with some portion of the graph. We calculate a message that leaves that portion of the graph and goes into another portion. And that message is a summary of everything we've computed from this portion of the graph about the joint distribution of whatever variables are shared between this portion and the portion on the other side, right? So that's the 1,000-foot summary of the last 4 or so lectures. I figure it's a good point to, now that you have it swapped in, a good point to stop and ask about residual questions about graphical models, variable elimination, belief propagation, messages, all of that sort of, all of those topics. So any questions? All right, I realize that summarizing 4 lectures into the first 5 minutes of one class might be a little whirlwind to prompt good questions. So if you can't think of good questions now, think about these concepts that I've been talking about: messages, belief propagation, variable elimination, independences, conditional independences. Formulate questions and ask them on Piazza. Right, and we'll do our best to have a good discussion of those ideas. All right. So there's one last topic for graphical models, and that's okay. If you have really big graphical models, even the graphical model representation of the world can be a little too complicated to think about. And so for big domains, like an image, for example, or a large collection of text documents, what people will often do is they'll use a shorthand for constructing big graphical models. And that shorthand is called plate notation. So it's maybe easiest to do it by example. So let's suppose that we have one random variable, which I'll call mu, and then a bunch of random variables that I'll call xi. I equals 1 to n, right? And what we'll do is we'll draw a plate around variables that are repeated, right? So what I've done here, it's like a for loop, right? Or a macro in a C preprocessor, right? The idea is that there's one random variable mu, and then the I equals 1 to n means that n times we're going to replicate the structure that's inside the plate, so we have n copies of the node xi. Right? And then there's an arrow going from mu to xi, and what that means then is we're going to construct a graphical model which has mu, right, and then x1, x2, x3. Let's say n is 3. Right? So it's going to correspond to this graphical model. Right? So that makes sense? So you can see if we have a big graphical model, it's going to be a lot more compact to write down using plate notation. And so, for example, if you describe it in a paper, the reviewers are going to have an easier time telling what you mean from the top diagram than from the bottom diagram. Okay? So to be more concrete, the sort of thing that you might imagine would be, let's say mu is a global mean that we don't know, and xi are each real-valued random variables that are normal with mean equal to mu. Right? So this describes a statistical inference problem. You could, for example, do it this way, right, with xi shaded. And what that means, that describes a statistical inference problem that we're all pretty familiar with, right? We have n examples of random variables with an unknown mean, and we want to infer something about the mean. Right? For example, its posterior distribution. So a lot of times we will also, when it's clear from context, we'll we'll just do something like this, mu xi n, right? So we'll just say n instead of I equals 1 to n when it's clear what the index and the bounds are. The other thing is that the plate notation describes the structure only, right? It doesn't describe anything about the parameters of the model. Unless you make the parameters be explicit nodes, right? You could say that mu is a parameter, but it's being represented as a random variable here, right? So you can represent parameters by giving them nodes, or you can leave the parameters implicit, right? So in each of these conditional probability distributions represented by the arrows, there could be parameters, and usually there'll be some accompanying bit of text with a graphical model that says what the form of the conditional probability distributions is, or what parameters are part of those conditional probability distributions. So does the idea of a plate model make sense? Cool. So you can do more complicated things with plate notations. So for example, you could have, let's say, a probability pi I and a mean mu I, right? And those are random variables, and they're going to be inside a plate, right? And so let's say we're doing a clustering type model, right? And there are k clusters, right? Then we could have an indicator variable, zi, or zj, which says what cluster example j belongs to, and then you could have xj, right? And that would be the actual observation of example j, right? And then there are n of those, right? And then the probability affects what the cluster indicator is, and the mean affects what the example is, right? So this is an example now of a graphical model with two plates, and the two plates don't overlap, so you just replicate k times the top structure, you represent n times the bottom structure, and then any of the arrows in between plates, you make them into a complete graph, right, with k nodes on one side, a complete bipartite graph, with k nodes on one side and n on the other. So for example, this is going to get kind of big if I try and do it pi 1, pi 2. Let's do it like this. Pi 1, mu 1, pi 2, mu 2, and then x1, z1, x2, z2, x3, z3, right? And pi 1 influences z1, z2, z3, mu 1 mu 1 influences x1, x2, and x3, right? And then pi 2 influences, right? And you can see, right, even for this tiny example, this is getting really kind of cluttered. But that's what it's equivalent to, right? If you have k equals 2 and n equals 3, right? And so 2 and 3 are very small numbers, and you can see that's already kind of a spaghetti mess, right? And so if you had 100 clusters and 1 million examples, it's pretty clear that plate notation is a good idea, right? Let's see. The next thing that we might want to consider are nested loops. So imagine, here's another model. We have a global mean mu, right? And then there's going to be, let's say, a bunch of groups which will be represented by j, right? And then, and each one of the groups will have a mean, right? And then there'll be observations. There'll be observations within each group. So they'll be indexed by group and by observation number within the group, right? And so mu will influence mu j, which will influence xij, right? And then mu j and xij will both be replicated according to the number of groups, which let's say that's k. And then, right, xij will be replicated a number of times. All right, I haven't left myself enough space here, but we'll put the n in the top corner, right? So there's n observations per group and k groups, right? And so we have, this is like nested for loops, right? And we create, I'm not even going to draw this out because I'll bet you guys can draw it out. But we create a graphical model structure where some of the structure inside each plate is then replicated an additional number of times for each plate. And just to get even more complicated, everybody's favorite example of collaborative filtering. Let's say we have a bunch of users and a bunch of movies, and every user rates every movie, right? So we could have user-specific variables, let's call them UI, and movie-specific variables, let's call them MJ, and then there'll be a rating, which will be Rij, and the rating will be influenced by both the user-specific variables and the movie-specific variables, and we'll have plates that look like this, right? So K movies and N users, right? And so this corresponds to a big square matrix where we have, let's say, rows corresponding to users and columns corresponding to movies, right? So do all of these sort of examples of the plate syntax make sense to people? Cool. So I wanted to just give one example of the sort of model that you can write down very easily with this plate notation, and that is a mixture of Gaussians, right? So here if we have cluster indicators Z that are discrete with a given probability distribution, and then parameters for each cluster, mu and sigma, right, and pi, which is the probability of that cluster. And so mu, sigma, and pi together determine ZT, which are the indicators of which point belongs to which cluster, and xt, which are the actual observations. And so here I've given an example where we have 3 clusters colored red, green, and blue, and I forget, it was like 50 observations per cluster. I forget what the number was. And so, right, that's the sort of thing that you can represent very easily. Maybe even more typically is that we don't know the cluster indicators, right? So I've erased the colors. And so what we have is that only here the x's might be observed, and it might be our job to infer pi, mu, sigma, and z, right? All right. So there's, interestingly, if we go back to this slide, right, where the cluster indicators are observed, this is a graphical model that we also have some experience with. This is the naive Bayes model, right, where Z is the class, X is the observation, and we want to figure out the parameters of each class, which are mu I, sigma I, and pi I, right? So if both Z and X are observed, it becomes naive Bayes. And if only X is observed, it becomes a clustering problem. And you can see, right, it's not at all obvious from the black how to split this up into clusters. But you know, there are some algorithms, which we may get to in future lectures, about how to do that. Let's see. And let's skip that and just mention that in addition to clustering of real valued variables, you can cluster discrete variables. And here, this is a mixture of multinomials instead of a mixture of Gaussians, right? So you can say that each multinomial is a distribution over the words in a document. And then every document, we select which one of the multinomials is used to generate the words in that document. And yeah, we have a nice document here about any of you who have flown recently will probably know that this is far too realistic a document, even though it comes from the Onion. And so this is called the single topic model because every document is assumed to come from a single topic, right? So the multinomials over words are called topics, and then we assign one topic to each document. There are much more complicated models that give multiple topics to each document and have some kind of structure over how the topics are related to one another. The simplest of those is latent Dirichlet allocation, but then you can get to fancier ones like Pachinko allocation or hierarchical Dirichlet process models, right? Like there's a ton of different ones, and you will see plate notation in a lot of the papers about these to help you describe what it is the model, what it is that we're assuming about the relationship between the documents and the topics. All right, so I think that's where I wanted to stop on plate notation and the very brief overview of mixture models. Are there any questions on these topics while we're swapping lecturers? Cool.
All right, I think the display is not responding, so we'll probably do it on the board if there's anything that comes up that I need to explain. Yeah, it's not switching to either the laptop or the.
Did it have my slides on it?
Oh, did it actually? No, it wasn't even down. Yeah, you were only using one, I think. Yeah.
Okay.
I can see it here, but I can see it switched to laptop in the projector, but it's just not showing up. Okay, so hopefully, yeah, we can do it on the board, but I have most of the stuff on the slides as well, so maybe it'll be okay. All right, so we are going to take a break from looking at different algorithms, more and more new algorithms so far, trying to model distributions, classifiers, regressors. You've done density estimation, lots of different stuff, but we are going to talk about the theory behind some of these, or how can we actually understand how good is a classifier, for example, that we have built, all right, and how can we understand it more formally. So, let's see, hopefully this will, yep, all right. Okay, so yeah, we have seen many ways of learning from data, and today we are going to talk about how good is our classifier, and in particular, how does the performance of a classifier depends on the size of the data set that you give to the classifier. So as you take more and more data points, you expect your classifier, more and more training data points, you expect your classifier to perform better. And can we formalize that relationship between the number of samples and the error that you can achieve using a classifier? And what can we say about the bias variance trade-off? We have talked about it many times now, and we have shown you some bounds which capture how far the true error is from the training error in terms of number of samples and often the complexity of the model space. So we'll be talking about how do you measure complexity, and how does the error of a classifier depend on both the number of data points as well as the complexity of the classifier. All right, so that's going to be our goal. And we'll start with a very simple setting. So most of the stuff we'll talk about for theory is going to be on classification. There are extensions to, of course, regression and other settings, but this is the simplest setting to study. So we have the following setup. We are going to assume we have m IID data points. So we are going back to the IID domain, which is a break from graphical models where we are trying to model dependencies. Okay? And we assume that we have a finite number of hypotheses to start with. So by a finite number, I mean that the total, if you're considering a class of hypotheses, for example, we can say, and hypotheses and classifiers are really the same thing. So we are talking about, for example, decision trees is one example of a certain depth. Then you can think of all possible decision trees you can come up with that have depth d, right? They are a finite number. That's one example we'll start with. Then later on we'll talk about what about a hypothesis space or a set of classifiers that are not finite in number. So what would be an example of a hypothesis class that's not finite? Something that you have seen before in this course? So I gave you one example of a finite hypothesis class, right? Just decision trees. You can build them up to depth d, and you give them the labels different leaves, and you arrive at a class of decision trees of depth d. What is an example of a hypothesis class you have seen that's not finite, that can have potentially infinitely many classifiers? Any thoughts? K-nearest neighbor would be yes, because there it depends on the number of data points, I guess. Yeah, you can call that infinite. Other possibilities, yes? Maybe Adaboost would be one, yep, because you're yeah? Linear? Yep, linear. That's another simple example, right? You're allowing for all possible lines. There are infinitely many of them, right? So these are all great examples, yeah, but they're all infinite hypothesis spaces. So we'll get to them later on, but we'll start first with something which is just finite. Okay? And the simplest bounds can be set for this setting. Okay, so continuing with our simple setting, we'll consider initially that we get to pick a classifier. So there's a learner, and he picks a classifier that is consistent with the training data. So the word consistent is used to mean it achieves zero training error. Okay? So let's say that we chose a classifier that had zero error on the training data set, right? And the question we'll want to answer is, what is the probability, what's its true error? Or actually, what's the probability that its true error is more than epsilon? So we know training error is zero for the hypothesis we picked. What's the probability that its true error is bigger than epsilon? Okay, so let's start thinking about this. And of course, you should all remember that even if a classifier makes zero training error, it can make more than zero test error, right? That's the whole idea behind overfitting and generalization and so on. All right, so let's think of it this way, that we have how likely is a bad hypothesis to get m data points right? Right? Because I told you that I have a classifier, the learner chose a classifier that got all the training data correct. So let's define a bad hypothesis as one that actually gets true error bigger than epsilon, and see how likely is it to actually be able to get zero training error. So we're just flipping the question around, right? That's something we can actually do a compute. So let's look at what's the probability that the particular hypothesis, so now this is the bad hypothesis, which is characterized by true error being bigger than epsilon. What's the probability that this classifier gets one data point right? So by the way, true error here is just the classification error, so that's just the probability of error, right? So the probability of error of h is bigger than epsilon. What's the probability that it gets one data point right? Yes, yeah, so it's the probability that it makes an error is bigger than epsilon, so the probability it does not make an error is less than 1 minus epsilon, right? Okay, so it's less than 1 minus epsilon, so that's for one data point. Now we are asking what's the probability that it gets all of the m data points right? And these m data points are drawn IID. Yes? You have the answer? Somebody needs to speak up. So one data point, yeah? Yep, exactly. So you just multiply the probability, right? I get one of them right with, if epsilon is say 0.1, then I get one of them right with probability at least 0.9, and I get two of them right with probability 0.9 times 0.9, and so on. So we just get 1 minus epsilon to that. Okay, so what we have characterized now is that if we have a bad hypothesis whose true error is bigger than epsilon, then it can get zero training error with this probability, right? Okay, so what we are actually interested in is we have a learning algorithm, right? We have a learner that looked at a hypothesis class, for example, decision trees, and picked one decision tree, and that got zero training error. Now there could be many more. We want to know how good is the learner, not how good a particular classifier we chose is. So what we care about is what's the probability that the learner chose a hypothesis that achieved zero training error, but its true error was bigger than epsilon. Okay, so there can be more than one classifier that actually can achieve zero training error. So we need to account for all of those, right? So if we want to study how likely is a learner to pick a bad hypothesis, right? So the learner just chooses from a class, and he happens to get one that achieves zero training error. We want to say how likely is the learner to have chosen a bad hypothesis, right? Then we need to think about that there could be more than one bad hypothesis. So let's say there are k bad hypotheses, which means all of them have error bigger than epsilon. And there's a probability that each one of these could be consistent with the data points, could get zero training error. And we want to characterize what's the probability that the learner would have chosen a bad hypothesis which got all the data points right. Right? So how do we do this? We just look at what's the probability, right? So the learner could have chosen either H1, which is one of the bad hypotheses, and it is consistent with them data points. Or it could have chosen H2 and it's consistent with all data points, or it could have chosen HK, right? All of them like that. And then what we care about is just bounding this probability. This will tell us the probability that a learner, how likely he is to pick a bad hypothesis, any one of these, right? Okay, so what do we do? We have a probability of one event or another event or another event. We would like to know some upper bound on this, right? So one way to bound probability of A union B union C is just to sum them up, right? So it is slightly an over counting, but that's one. So one thing there that you should know about is when we are talking about coming up with bounds on how good a learner does, we can usually only come up with upper bounds. There are also lower bounds, but sometimes there is a gap between them. And proving lower bounds is much, much harder. We don't do that in this class. We'll talk about upper bounds on the performance of a learner. And if you want to see lower bounds, then you should take 702, which goes into much more detail. Those are much more complicated. But so far, it suffices. At least you have an upper bound. You know your classifier can never do worse than that much, right? It gives you a characterization. OK, so since we are happy with upper bounds, we can just upper bound this probability that the learner picks one of the bad hypotheses that happens to be consistent with the m data points by a sum of them. And this is known as, this trick is known as a union bound. You'll see it often. So it's a little bit loose, but often it gives meaningful results. All right. So we already know what's the probability that a bad hypothesis is consistent with m data points. We worked it out in the last slide, right? It was less than 1 minus epsilon to the m. And now we are just summing k of those. So we have a bound on this, right? It's just k times 1 minus epsilon to the m. Everybody OK with this? All right. So what we did on the previous slide, we said what's the probability that a bad hypothesis is consistent with the training data? Now we are saying what's the probability that the learner chooses a bad hypothesis that's consistent with the training data, and there could be many bad hypotheses in our class, right? So we are just summing over all of them. That's why we get k times 1 minus epsilon to the m. All right, so we would like, that's just a summary of what we did so far. Now we don't know what k is, how many bad hypotheses are in the class. So one way to do, since we assumed it's a finite hypothesis space, and again we are happy with just upper bounds on the performance, we could just say, well, we know that there cannot be more than the size of the hypothesis space number of bad classifiers. So again, it's a loose bound, but we can just say that the total number of bad hypotheses is bounded by, when I write mod h, it actually means the size of the hypothesis space h. So it's the total number of, for example, decision trees with depth t, right? So we can upper bound it like this. And there's this small trick which says that we can write 1 minus epsilon is less than e to the minus epsilon. So it helps us understand the dependence on the different terms a little bit better. So we arrive at this bound. So let's pause a minute and see why this bound makes sense. So what is it telling us? It's saying that the more the number of data points we have, which is the larger m is, the better is the bound, right? Or the smaller the probability that the learner picks a bad hypothesis, right? Which makes sense. Smaller we choose epsilon, right? So in fact, yeah, let's maybe, I think I have plots for these. So with m, as the number of data points increases, the probability that learner picks a bad hypothesis goes down, right? Which makes sense. Let's think about epsilon. Again, similar thing, as epsilon goes on increasing, the probability learner picks a bad hypothesis goes down, because we are relaxing the requirement on how bad the hypothesis is, right? We are saying it can be, as epsilon increases, we are allowing it to be more and more worse. And so the probability that the learner will actually pick such a bad one, and it will actually correctly classify all of the training points, is going to be small, right? So intuitively, that should make sense. And finally, the third thing is the size of the hypothesis space, right? And you can see that here, your error actually increases the larger the class you search over, which again makes sense, right? If we are requiring the learner to, if we allow it to look over a very, very complicated class that has lots of decision trees with very large depth, for example, versus very shallow depth, we know that we should be paying some price for it. So you see that again, the probability of picking a bad hypothesis increases with that. So this is one measure. The size of the hypothesis space is one measure of how complex the class is. And we have earlier talked about that as the complexity of the model class or hypothesis class increases, we see that our error becomes, at least there's a sweet spot where it's perfect, but then the more complex you choose it, the more worse is the performance, right? Okay, so hopefully this should make sense. Any questions on this? Yeah.
Can't you say, like, doesn't, you put h as like a big upper bound, but like, can't you just assume that there's at least like one good hypothesis and do h minus 1, or does that not work?
You may not know that, right?
Yeah.
So because this is, what is k? K is the number of hypotheses that have true error bigger than epsilon. There's no way to know that how many hypotheses will have true error. You may not have any good classifier, right? Depending on epsilon, right? Yeah, but you are right that actually we can improve on this as we'll go on in the course. We'll see that there are better ways to bound it than just the number of hypotheses. Right. But h minus 1 won't do it. Right. Okay, any other questions? Yeah.
Could you explain more about the middle graph, the epsilon?
Right.
I don't know why when the training error is high, then the probability to take a better hypothesis is low.
Because as epsilon increases, right, we are characterizing the set of bad hypotheses as ones which have true error bigger than epsilon. So we are saying these are the hypotheses. As epsilon increases, they have higher and higher true error, right? So what's the chance they'll actually get 0 training error? It's going to be very small, right? Does that make sense? So the bad the hypothesis is in truth, the less likely it is to actually get all the training data correctly. And that's what this is reflecting. Right? So because the learner chose it using, he chose a hypothesis which has 0 training error in this example, right? So the probability that he'll pick such a hypothesis is going to be small because its true error is much larger. Yep. Any other questions? Okay, so let's summarize this. And what we just derived is actually known as a PAC bound, which stands for probably approximately correct bound. Okay, and this was derived by Hostler in '88. So here's the formal theorem, but we'll talk in a minute about why it's called PAC. So it's if you have a hypothesis space that's finite, for example, again decision trees with finite depth, and you have a data set with m IID samples, and some target you want to bound that your true error is less than some epsilon, then for any learned hypothesis that's consistent with the data, training data means it gets all the training data correct, the probability that its true error is bigger than epsilon is less than this quantity we just derived, which depends on the size of the hypothesis space, the number of data points you have, and of course the accuracy control you want on your true error. Right? And the reason it's called probably approximately correct is you can think of this, I can upper bound this by delta, or if it helps set it equal to delta. Then there's a reverse way I can write this statement. I can say that with probability bigger than 1 minus delta, my true error is less than epsilon. Right? So I'm just redefining, you can think of it as redefining this as delta. Then here's an equivalent statement. And this statement, as you can see, is a probability, right, with high probability. Your hypothesis is correct, but only approximately. So that's why it's called a probably approximately correct or PAC bound. Right? With high probability, the true classifier is approximately correct. Okay? Yes?
So just to clarify, does this assume that the true hypothesis is in the hypothesis space? Like, I mean, let's say that it's not, it doesn't give you any, it doesn't tell you how assured you can be if the hypothesis is actually in the hypothesis space, the true hypothesis.
Right. This is not assuming that. Right? Yeah. But we are saying we are only characterizing the true error of the classifiers which get 0 training error. Okay? So yeah, we'll talk about next about what can we say more generally about other classifiers. You may not be able to find a classifier that achieves 0 training error, and we'll talk about what happens then. Yeah.
But I think what you're asking is what happens if there's no classifier that achieves 0 test error. That's
Yeah.
what you're asking.
Yeah.
Yeah, so we don't have to have such a classifier because there's no place in the tool where we assume that.
Well, even training error, what if you can achieve 0?
Yes, that's what we'll get to next. But yeah, Ara was also clarifying that we do not assume that you have a classifier that can get 0 test error, whose true error is 0. That's also not assumed. Right? We are just saying that if you happen to find a hypothesis or pick a hypothesis that has 0 training error, we can say how bad its test error is going to be. Okay, or at least bound it with high probability. All right. Okay, so yeah, and just a note here that we can prove such bounds. Of course, that does not give you a way to find the best hypothesis. We are just saying if you happen to find one that has 0 training error, you have a bound on its performance. Okay, so it's not giving you a procedure to find the hypothesis. It's just helping you quantify it. So of course, in practice, you may not find one with 0 training error, and we'll get to that in a minute. But here are some equivalent ways of using this pack bound. So how can you use it? So there are different ways. So suppose, essentially there are three quantities that are involved. There's an epsilon you can specify. What's the control you want over your true error? There's a delta, which is with what probability you want your pack bound to hold. And then there's the number of samples. So very often people talk about what is known as sample complexity. And then what they're saying is that you specify epsilon and delta. You specify the accuracy you want and with what probability you want the bound to hold. And then you ask how many training data are needed to get the error to within epsilon with probability bigger than 1 minus delta. So that just involves flipping. So notice that we define this up, like that's how we define delta. So you just flip this inequality around and get a lower bound on m, right? And you can see, so yeah, that's maybe something we can quickly look at, but just flipping it around, right, we get, so I can write e to the minus m epsilon is less than delta over mod h, or e to the m epsilon is bigger than this over delta, and taking the natural log, we get log of this plus log of 1 over delta, and this gives you the m, right? So you should be able to like flip these things around, and if you're given delta and epsilon, you want to find how much data you need, it gives you a bound on it. You need at least this much data to guarantee that with probability bigger than 1 minus delta, your true error is going to be less than epsilon. All right? Of a classifier that achieves 0 training error. You can also look at it another way to say that if you're given the number of data points and given with what probability you want your bound to hold, then you can actually say what your bound should be. Right? So it's again flipping it around, but this time writing epsilon in terms of the remaining terms. Okay. So there are different ways to use this bound. In particular, this one is useful. As I said, it's called sample complexity. It tells you how many data points do you need to ensure your classifier has a certain performance. Right? Yes?
So I'm just curious, how does this relate to like classical statistics where like a p-value like p less than 0.05, kind of a thing? Is this similar in the sense that it's giving you some bound on your confidence of the?
Well, I would think of this as a bound on, like in statistics, you would have a bound on regression error. This is a similar bound on the performance of the classifier here. So it's a bound on the classification performance. With respect to p-values, those are for testing, right? So we don't necessarily have a test here, because if you have a test, then you have to assume a null hypothesis and a null distribution, and the p-value is based off of that, right?
So there is at least a small relationship, which is, if you think about like the p-value for a confidence interval, that's the probability that your confidence interval fails to cover the significance value. Alpha is the probability that your confidence interval fails to cover the true parameter, and here there's a failure probability delta, right? So it's the probability that that your guarantee on the accuracy of your hypothesis fails to hold. But you're asking a different question in the two cases, right?
Yeah.
It's that your accuracy is much worse than you said it was, or that the parameter is outside some region where you said it lay. Right?
Right, yeah. Yeah, they're asking.
And this is like a power analysis, kind of, where you're trying to
Yes.
estimate
Yes.
how many samples you need.
Yeah. Right. Yeah. Yeah, again, because there are no two hypotheses, you're just assuming a model, and under that you're showing what the performance is. So yeah, if you want to think of your H1 as the true, then you're sort of doing a power analysis. All right, any other questions? Okay, so yeah, let's talk about the limitations. And as some of those you already pointed out, one is that this bound is only holding for classifiers that achieve 0 training error. So only if you can find such a classifier, you can use this result, the Hostler's bound. And another is the dependence on the size of the hypothesis space. As we talked about, there are hypothesis spaces like linear classifiers, like K nearest neighbors, and so on, for which the hypothesis space is too big, or it could be continuous. And does that imply you need infinite training data to guarantee a certain performance? Seems like that shouldn't be the case, right? So the bound, as we said, this is just an upper bound. So can we tighten it somehow for such hypothesis spaces, which are not finite? Okay. All right, so we're going to tackle both these issues. This is just, again, a reminder that if you want to, the Hustler's bound only applies for finite hypothesis spaces. Examples, I've been talking about decision trees of a certain depth. There could be decision trees of a certain number of leaves. There could be histograms with a certain number of bins. All of those would fall in this category. Again, there are different ways to state it, but we are going to just keep adding to this list of all the bounds we come up with. So you have seen the Hustler bound, which looks like this and only applies to hypotheses for which the training error is 0. Okay? And we'll go on adding to this list as we go further. So let's talk about what happens. Can we say anything about classifiers that may not be able to achieve 0 training error? So what if we are able to find one that has training error, which we'll just write as training error, right? So it could be whatever number, right, which is not 0. So we can still analyze what its true error should be. Of course, how far it can deviate from the training error, right? And the way we do this is we think about the error as actually trying to estimate the bias of a coin. Okay, so why is that? Because what's error? It's just the probability that the predicted label matches the true label or not. And we can map it to thinking of, we toss a coin, and what's the probability that it turns up a head? If the predicted and true labels match, we say that that's a head. If they don't match, we say that's a tail. Okay, so with this correspondence in mind, we can try to think of writing the true error, which is probability that the predicted label h of x does not agree with y, as probability of a coin showing up heads, okay, whether the labels match or not. We've converted that to a head or tail problem. And what's the training error? Well, that's just empirically counting how many mistakes you made on the training data set, right? And we'll think of that as coming up with an estimate for what's the probability that the coin will land heads. We just do a bunch of such coin flips on our data, right, whether we can match its label or not, and we just do an empirical average, right? That's how you would have done the estimate of the head of a coin toss, right? If you wanted to estimate what's the probability of a coin turning head, you toss it a few times, and you just take sort of the average of how many times it came up heads. So that's how we'll try to think of true error and training error. And once we write it like this, then there's a concentration result we can leverage, which goes as follows. So this is known as a Halflings Bound, and what it says is that if you have m IID flips of a coin, right, where I'm thinking of xi's as being either 0 or 1, tail or head, right, and the coin has a parameter theta, which is the probability of it turning heads, then we can quantify how far is theta, the true parameter, from the empirical estimator that you might come up with, just the average, right? So how far is the empirical average from this true average, right? And we can quantify, we can say that the probability that the difference exceeds epsilon is less than 2 e to the minus 2m epsilon square. Okay? So such kind of concentration results exist and have been proved, and there are many more that you can look up with. This one suffices for our purposes. Right? But it's telling you how far is an empirical estimate from the true parameter, at least as far as when these variables are just coin flips, okay, binary variables, 0 or 1. So we can take this and we can apply it to our true error and training error. So instead of theta, as we said, like theta will replace with the true error, and the empirical average theta hat will replace with the training error, right? So if we do that here, we replace theta with the true error, this thing with the training error, and now we can say that the probability that the true and the training error differ by more than epsilon is bounded by this quantity, 2 e to the minus 2m epsilon square, for a single hypothesis h, right? Because for every hypothesis, we can replace its true error, we can associate it with a theta. If we have a different hypothesis, we will replace its true error with another, right? So, but for a single one, we get this bound. And again, we would like to make a guarantee about not a single hypothesis, but about a learner that picks from a class. So what if we are comparing, if we are picking from h hypothesis to pick one, then for each hypothesis, we have a bound like this. We would want to give a performance guarantee on the learner. So we do something similar. We use our union bound technique, right? Now we can say that probability that the true error and the training error for mod h number of hypotheses, probability that all of them differ from, or the difference is bigger than epsilon, you can, or for any of them, I should say, not all of them, for any of them it differs by epsilon, can be bounded by just you include the size of the hypothesis class here in the bound, just as we did earlier, right? So you end up with 2h e to the minus 2m epsilon square. And again, there are different, this bound should look very similar to what we had before, except earlier the training error was 0. And in fact, if you have a sharp eye, you would have seen that there's one more difference. We have an epsilon square instead of epsilon. So there's still, you can quantify how far they are. The dependence is slightly different depending on whether your training error is actually 0 or not. Okay, but you can, by writing it less than delta, you can again flip it around and make it a packed bound. You can say with probability bigger than 1 minus delta, the true error is within training error plus minus epsilon, essentially, right? Once again, the reminder that we can have a bound like this, it still does not guarantee that you will pick a hypothesis which has a certain, which has the best performance. It just says that if you chose a hypothesis with a certain training error, it tells you how far the true error can be. Okay? So again, this is what we had earlier, the Hausler's bound. If we compare the bound we just derived, which is known as Halflings bound, and we write it again in a with high probability kind of statement, bigger than 1 minus delta, then we have that the true and the training error can only differ by epsilon, which now looks like this. So notice the difference is again a square root term, which comes from because the bounds had epsilon versus epsilon squared, right? So it's slightly worse, the square root is slightly bigger, right, for things less than 1. So it's a slightly worse control over your true error, but you can still control how far true and training error are. Question? Yeah. So the reason is that you're sort of only doing one-sided control. Part of the reason is that, right? Because you
well, one-sided control is the reason for that factor of 2, right?
Oh, actually, you're right. Yeah, yeah. So there's the 2. You're right. That is the difference. The not square. The reason is it essentially has to do with that if you're estimating the bias of a coin and you're near 0 or 1, it's easier to do it than in between. I don't know if I can give a better explanation at this point.
Yeah, there's got to be a way to interpolate between these two bounds, but I don't know it, right? So for very small epsilon, that bottom one has to be conservative.
Right, yeah.
But I haven't actually seen anybody write this sort of interpolated bound.
I think I tried it once, and it has to do with how close you're, how close you are to one of the two edges. Right. Like your empirical error is going to be 0 only if your true error is close to 0, and if you're estimating things closer to 0, it's a little bit closer to 0 or 1. You're sort of more sure, so it's a little bit easier. I know it's not a very appropriate explanation, but
yeah, I mean,
yeah.
The sort of the vague explanation is that, okay, we're making some approximations in each of our bounds, right? And each one of those approximations loosens the inequality, and the approximations are very loose near 0 and 1, and so we could have made a tighter one if we had been willing to deal with a more complicated expression.
Right. Yeah. Maybe I can think about that and get back to you if I find, if I can nail down exactly, okay, this is the place where we made it looser, but yeah, off the top of my head, that's all I remember. That had to do something with how close of a quantity near 0 or 1 you're estimating. All right, any other questions? So let's look at these bounds again and see how that actually relates to the bias variance trade-off we have been talking about, right? So we talked about how as you increase the size of your hypothesis class, as you allow more and more complicated predictors, at least as you increase the size of the hypothesis class, that's one outcome you get, that you get possibly more complicated predictors, and how that gives you the bias variance trade-off. We have talked about that. How you can understand it from this expression is as follows. Again, we can write it as saying with high probability, bigger than 1 minus delta, the true error is less than training error plus epsilon, which is this quantity right here, right? So clearly, as the number of data points increases, the true and the training error, they become closer and closer. As the model complexity increases, they get further and further apart, right? So this should remind you of the figure we talked about, I think a few lectures back, where we were drawing versus model complexity. So here you can think of the model complexity as characterized by the size of the hypothesis space. The training error keeps on going down, right? But the true error has another behavior. Right? So it has a sweet spot, but this is just an upper bound, so it shows you that as h increases, the true error deviates more and more from the training error. So right, yeah, so maybe you should think of this as, this expression tells you the difference between these two curves, and the difference always goes on increasing as the size of the hypothesis space increases, right? And so yeah, here's another way to think of it. If your hypothesis space is very complex, right, then your training error should be close to 0, right? It should be very small. Whereas here, how far your true error can be from the training error could be large, right? And another way to think of this is you're really searching over a hypothesis space, right? So suppose I draw a big circle to indicate your hypothesis space H, right? Then you are paying a price for searching in a larger and larger space, right? And that's what governs how far the training and the true error are, right? And if it's simple, it's vice versa, right? So you can see sort of that bias variance trade-off from this expressions also. All right. So if there are no questions, let's get to the second limitation of Halflings Bound. So first was that it only applied to classifiers that had 0 training error. We have fixed that. We also need to fix what happens if we have hypothesis spaces that are not finite, right? So let's get to that. And to understand that, actually, we should let's look at one example and see actually what is the size of these hypothesis spaces, right? And the running example we have sort of been talking about is these decision trees. So let's look at decision trees of depth k, let's say, and let's try to look at how many such decision trees can there be. Okay? So before we get into it, just wanted to clarify a few things that, of course, decision trees can be defined many ways. So let's focus on decision trees built on binary features only. Okay, for simplicity. So say we have n binary features or attributes, and let hk be the number of decision trees of depth k built on the binary attributes, and we are going to think of only binary decision trees, right? So binary attributes, it's easy to see. You're just splitting on each feature once, or not once, but like you're only at one time you're only splitting on one feature, just going by the 2 values it can take. That's the simplest setting to consider. All right, so we are going to come up with, we want to get a sense for how large this hypothesis space can be. Okay? So let's think about H naught. So that's a decision tree with depth 0. How many decision trees are possible with depth 0? How many people think it's 1? How many people think it's 0? How many people think it's 2? Anybody for more than 2? Okay. What's the right answer? Okay, so we are talking about how many decision trees, right? So you should think of not just the tree, but the assignments, the label assignments. So it's one tree because you have one leaf, and you're everything that's in that leaf, all the points, you're just assigning it one label, but there can be 2 labels. So the correct answer is actually 2, which nobody got, or I don't know if somebody got it but didn't raise their hands. So you can either assign everything a 0, or you can either assign everything a 1. So there are 2 decision trees possible of depth 0, right? Yeah, so that's 2. Now to derive how many decision trees of depth k, in general it's hard, but if we do it recursively, it's easy, right? So let's try to write how many decision trees of depth k in terms of how many decision trees of depth k minus 1 can there be. So what should the expression look like if I wanted to do that? So let's first think about what happens. So suppose we have a decision tree of depth k minus 1, and I'm now creating the next depth. So I can pick amongst any of the attributes to split on, right? So there are n possible choices for me at that point, right? So different ways you can construct a decision tree of depth k from a tree of depth k minus 1 is by picking any of the n attributes. And anytime you pick that, now you can have you essentially have, so it's the number of choices here of the root attribute plus number of times possible left subtrees and number of possible right subtrees you can get, right? Yeah, so you can write hk as just n times hk minus 1 times hk minus 1, right, which is the number of decision trees of a certain depth.
It should be a less than or equal to, right? Because you can't split twice on the same binary attribute.
No, you can, right?
Well, but it doesn't make a distinct hypothesis.
You mean you can't do it immediately, but you can, if you are reusing attributes, you can, right?
Well, you split on, let's say, x1, and it's true. Now, in the tree down below it, every time you test x1,
You just,
it's
oh yeah,
true.
okay, yeah,
So it should
right.
be less than or
I see
equal
that's,
to as
yeah,
opposed to-
sure. Yeah, I guess I was still thinking of, yeah, these are, I specified these are binary attributes, as you
Right.
say, yeah. If you have continuous, then yeah, you can,
Continuous,
you're
you
right.
can resplit.
Yes, yes, okay. Right, so this should, I guess, be an upper bound. Okay, that's a good catch. Yeah, but I guess we'll be happy with, we just want to get a sense for how large, basically want to get a sense for how large can the space be as a function of like the depth in this case, k, right? Okay, so now we have a recursive relationship, and now we can get, actually we know what the initial point is, right? So we can try to get a sense for how large hk should be. And because it involves products, a good way to do it is, let's do it in terms of log, then everything becomes a sum. So I can write Lk as a log of the number of trees of size of depth k. So L naught is just 1, right, because h naught is 2, and I'm taking log to the base 2. I can write Lk, right, so Lk is log of this quantity, which is log n plus twice log hk minus 1, which is twice Lk minus 1, right, so I get the first part. And then I can just recursively keep on writing Lk minus 1 in terms of Lk minus 2 and so on, right, so that's what I did here, and you can keep on expanding it. Now you just get a series here that you can sum up. So I believe the way you would get it is you can pull out all the logs, right? So then I'm left with, once you've pulled out the logs, you're left with, I guess 1 plus 2 plus 2 square and so on up to 2 to the k minus 1, yep, right? And then the only term that didn't have a log is the last one, right, which is 2 to the k minus 1 times, you have 2 L naught, but L naught is 1, so I can just put a times 2 there, right? Okay, so this part is just 2 to the k minus 1, right? I believe, yeah, that's true. It's just a geometric series, right? So we get, yeah, so we get 2 to the k minus 1 times log 2n, and I think we should have plus 2 to the k. I don't know if that's what I have here. Yep, that's what we have there, right? So it's 2 to the k times log n, and then the rest is just 2 to the k. Okay, so we now have an expression for the log of the number of trees of depth k, right? And the reason we wanted to derive this complicated expression, which I'll rewrite here. Okay, yeah, so I guess the way to, the reason we wanted to do this is you can see that the log of the number of trees of depth k is like 2 to the k, right? So we want to see the dependence on the depth. So if I look at the number of trees of depth k, that's 2 to the 2 to the k, right? That's a huge number. And if I plug that into my bounds, which involved, which tells me how many samples I need to guarantee a certain error, that involves log of h, so that is like Lk, that's still exponential in the depth, right? So it's saying that the number of training points I need to guarantee a certain accuracy, epsilon accuracy with probability bigger than 1 minus delta, scales exponentially in the depth of the tree. So that's a huge number of data points to have, right? So that's really bad. Yeah, that's what I have here, where we just plugged in log of h with that exact expression. But you see that it's exponential in k. So the total number of data points you need. Now clearly that's bad, right? Why? This should be sort of counterintuitive in some way. Can people think of why? I give you m data points, and I'm learning a tree on that. In some sense, how many? If I give you m data points, can you build a very, very deep decision tree? You're ultimately limited, right? You don't want to just keep on creating empty leaves. So if you're given m data points, you believe that there should be maybe a reasonable limit on how many decision trees you might have, and hopefully not exponential. Right? So the decision tree in some sense shouldn't be getting too big if we have only m data points. Okay. All right, so maybe we are sort of overcounting in some way, or maybe there's a better way to think of how complex the decision tree class is. And we are essentially going to go by this, that we know that the number of leaves should never be more than number of data points, right? If you're building a decision tree. So maybe the right way to think about it is not in terms of how many trees of a certain depth. There can be many, but most of them are going to be useless because they are just not giving us anything meaningful. They're just giving empty leaves. We are splitting on empty leaves. But we should think about how many decision trees there are with a certain number of leaves, right? Because given m data points, we cannot have more than that many leaves. All right. Okay, so let's redo the calculation, but now thinking about how many decision trees there are with k leaves. All right, h1. So now I'm calling it h1. It's the same that we had earlier. When I have only one leaf, it means I'm assigning the same label to all the points, right? So again, I can have two decision trees, one that assigns everything a +1, and another that assigns everything a -1, or 1 or 0, whatever you want to call it. And now we are again going to write a recursive relationship, which is a little bit more complicated, but hopefully it will make sense. We are going to write how many decision trees with k leaves in terms of how many decision trees with fewer leaves, okay? And it's a little complicated, but once you stare at it, it will make sense. So again, we are going to have as many attributes as we have as the choice of splitting. So we have a tree with k minus 1 leaves potentially, or maybe let's say we are starting out. We need to split along any of these n attributes, and what we end up with is either a left subtree with 1 leaf, and the right subtree will have k minus 1 leaves, right? Or the left subtree can have 2 leaves, right one can have k minus 2, and all possible combinations, right? So the total number of leaves after we do the split should sum to k. So that's all the possible ways in which you can create a decision tree of k leaves, right, from a previous step, right? So this is splitting on 1 leaf and 1 tree, k minus 1 in the other, 2 here, k minus 2, and so on. All right, so if you write this recursive relationship out, that sort of looks like this. It's n, which is the number of attributes, times we are summing over how many things can go to one of the leaves or to one of the subtrees, which can be either 1 to k minus 1. That's the number of leaves in left subtree, times the number of such trees, and the other one is just the complement, right? So the right subtree can have k minus I leaves if the left one has I. So this is the recursive relationship, and this one is actually not that easy to compute, but this is actually known, and we won't go into it, but you can look it up. This is actually can be written as n to the k minus 1 times something, which is the Catalan number for trees. Okay, so it's essentially about counting trees, and here's actually a loose bound on it. Okay, so it essentially looks like the total number of decision trees with k leaves actually looks like this. And notice that this is exponential, but we are talking about the number of decision trees, not the log of that, right? So the total number of decision trees now is exponential instead of super exponential in k. And if we plug that into our requirement on the sample complexity, the log of this thing, we get something that's linear in the number of leaves, right? Log of this quantity is linear in k. Right? Yeah.
The way to think about this is your original thing was how deep are decision trees, right? But it seems like that depth is only ever going to be larger than the number of data points. Makes sense, right? It doesn't really make sense to go further than that because then you're just splitting.
Well, but you could have I mean, that's sort of sided intuition, but you could build a very, very one-sided tree, right? So your depth can potentially still be equal to the number of data points if you do that. But if we are, that's what, yeah, so the number of leaves is what's tied to the number of data points, and that's what should govern the complexity, not that if you have a very, very one-sided tree with m data points, you don't want to take into account all the other decision trees which might have other unnecessary splits, right? That are just splitting empty leaves, essentially. So that's the moral of the story here, basically, that we should be thinking about the complexity of decision trees by how many leaves they have, which is related to how many data points there are, as opposed to the depth. So if, yeah, as we saw that if you do this, you get that the number of data points you need to train such decision trees is only linear in the number of leaves, whereas it was exponential in the depth. Okay, and the first one sort of makes more sense. So we are actually, let me skip this. It's just yeah. So I sort of wanted to end at this kind of idea that what we learned from decision trees is what we are going to build on in next class to think about the complexity of hypothesis space that are not necessarily finite. The idea is that the complexity of a hypothesis space or of learning should be measured in terms of not the size of the hypothesis space, but in terms of the maximum number of points that you can correctly classify using it, right? So why should we allow decision trees with k leaves or with m leaves actually if we have m data points? Because we can exactly, if we allow them with k leaves, then k is the number of data points we can hope to correctly classify, right? So that one lies in each leaf. So we should be thinking about, given a hypothesis class, what's the maximum number of data points that you can consistently classify using that hypothesis space? That's a better measure of the complexity of that class than looking at the size of that hypothesis space. So this requires some thinking. So if you didn't follow it, you should digest it a little bit before next class. But essentially, we are just thinking of, you can use the size of the hypothesis space. It will give you a bound, but it's going to be a very, very loose bound. As you can see with infinite hypothesis classes, it's going to say that you require infinite training data. Or as with the case of decision trees, it might say you require data that's exponential in the depth. But you can get a better bound if you think of the right way to characterize the complexity is by thinking of how complex of a hypothesis space you will search over ultimately depends on how many data points you have. And if you only have m data points, you only care about correctly classifying those in some sense. That's the maximum complexity you should be searching for. And so you should be tying your hypothesis class complexity down to what's the maximum number of data points you can correctly classify using a classifier in that class. Okay. So in next class, we'll build up on that. But I did want to just, I guess, go back and remind you of this. That again, you can, at least for decision trees, you can plug in, instead of the size, now we have derived two bounds on the size of decision trees with depth k or with k leaves. And with k leaves, you get complexity something like k log, it's linear in k, right? And you can again think of the bias variance trade-off that if k is m, the number of data points, then you can hope to get zero training error because each data point can potentially fall in one leaf and you can get zero training error. You can perfectly classify it. But if k is m, you see that this quantity is like essentially like close to half, right? Because k is like m, and assuming m is much larger than 1 and so on, you can see it's close to half. But if k is less than m, you have fewer leaves than number of data points, then multiple data points will fall into one leaf and you may not exactly classify them. So the training error could be greater than 0, but how far the true and the training error are can be small. Okay, so again gets at the bias variance kind of trade-off. All right, so we'll just end here. I think that's a good point to stop. And we'll talk about how to think of complexity of infinite hypothesis spaces next time.